Hi, this is Kevin Trainer. Welcome to my lecture for Chapter 4 of the Murach 3rd edition MySQL book. Chapter 4 is about how to retrieve data from two or more tables. And the metaphor that I use um, is that the Chapter 3 content, where we learn how to um, retrieve data from a single table, um, is kind of like the first step of trying to learn how to ride a two-wheel bike. And what a lot of people learn in that first step is to learn how to drive the bike, ride the bike in a straight line. Okay. Because the next skill that you learn, which is how to turn and lean and all that kind of stuff, is very complicating, right? So we typically want to make sure that you get the how to drive in a straight line first, and then we teach you about turning and leading and all that kind of stuff. So chapter 4 is the turning and the leaning. Okay. It's a complication of the simple stuff that we learned in chapter 3. It uses all of the elements plus these new elements that allow us to get data from more than one table. Now, why do we want to get data from more than one table? Well, it has to do with the way that the style of relational database design that we use. The tables are typically about one thing, one type of thing in the world that we're interested in. So we have an employee table. We have a product table. We have an invoice table. We might have an equipment table. Okay. And all the data in that one table is about that thing. Okay. Um, it's pretty, as ways of storing data go, it's pretty, it's pretty atomic, right? Well, then, if we're only storing the data about one thing in a table, well, then how do we put together the kinds of reports and screens and all that kind of stuff that we need to do some kind of business with that data? You know, how do we do the business of our organization, whatever type of organization that might be? Well, we combine data from more than one table. So uh, storing the data that way is a really good thing to do. But that's not typically the way we use it. And sometimes what I do is I use another metaphor for the difference between how we store data in a relational database and then how we use it. And it comes from family things, again, not quite as fun as learning to ride a bike. But uh, most families have a special set of dishes that they use for holidays and celebrations. Uh, Quite a few families do. Okay. And when they're having some kind of holiday dinner, they set the table. Here in the US, this might be American Thanksgiving, right? And we take out the good plates and we take out the good cutlery and we take out the good glasses, or the best we have. And we typically set each of the places with an assortment of all these things. Probably a bigger assortment than we're used to in your typical everyday meal, right? And so everything has its place, and they're all sort of arranged together. And that, you know, we typically set a place for everyone around the table. So let's say we have a big family and lots of friends. We have 12 people for this holiday meal. Well, then there'll be 12 place settings. Um, and they all would have this a carefully displayed array of plates and cutlery and glasses and all that kind of stuff, and maybe a napkin or something like that, right? Okay, but how do we store those? Well, typically what we do is that we store like things with like things. So after the meal's over, we typically, we wash up the plates and we dry them, let's say. And then we stack them up. The small plates go with the small plates and the big plates with the big plates and the forks with the forks and the tall glasses with the tall glasses. And we typically put them away um, in a pretty much like we do in relational databases. We have a place for the small plates. We have a place for the tall glasses. We have a place for the spoons. Okay. And even though they're not tremendously useful, um, it's stored like that, they do take up a minimum amount of space, and we do know where to go to find them. Okay. So, the metaphor that I'd like you to think of is these relational databases that are designed using a principle um, that we call normalization, in which the contents of each of the tables is only about one type of thing. They're kind of like the way we store the plates and the glasses and the spoons and the forks. Uh, each together in its own special spot. And yet, when it's time to have a holiday dinner again, uh, we don't use them individually. We go back and we assemble a place setting that might come from many more than one place in order to get the beautiful arrangement that we would like to have at the holiday table. So too with relational data and relational databases. What we're learning now is kind of how to take all these things out of the cabinets and set the places at the holiday table when they're all kind of stored individually. Okay, and in a pretty unuseful and unappealing way for us. Okay. All right, I promise that's the last of the metaphors for this chapter. So let's get started here. Well, there we go. So this chapter has lists of objectives and knowledge goals and all those things. As usually, I'm going to leave them for you to read on your own. So how do we combine data from more than one table? Well, we learned about the select clause in chapter 3. So here in chapter 4, we're learning that if you want to, say, get data from two tables, you make adjustments in the from clause. Okay, and instead of just saying from a single table name, we say from a single table name, join another table name. Now you may notice here that this says inner join, and inner joins are just regular old joins. We're going to learn towards the end of the chapter that there's a thing called an outer join. So people call inner joins in order to distinguish them from outer joins. But because inner join is the default, and because inner is kind of wordy and you don't have to use it, I like to tell people that inner joins are just plain old mom and pop joins, and we're not going to use the inner word in my class because it's just kind of verbose. Okay, so I would have said here, select invoice number, comma, vendor name from vendors join invoices on, and then we have an on condition. And then we say order by invoice number, and we get back, let's see, we get back 114 rows, okay? That's one row per invoice, okay? So we have the invoice number and we have the vendor name. Well, that turned out well. Now, it turns out that all of the invoices match a vendor, okay? Why is that? Well, because of the way that we define the database, and because of these things that we have called foreign key constraints, when you add an invoice, you have to provide a foreign key that points to a vendor. So, and if it doesn't point to a proper vendor, then your insert's going to fail. So when we inserted all these invoices, we hooked them up to a proper vendor, and now we can go through 114 invoices, and it's not surprising that they're still attached to the vendor that they were attached to in the beginning, right? So what we're getting is we're getting a row back for every invoice, and we're getting the vendor name on it. Now, let me ask you this. Are we getting a row back for every vendor? No, the fact is we're not, okay? I don't know exactly how many of the vendors we're using, but it's actually, I think there are 122 or 123 vendors. And we don't have invoices for all of them. And pretty soon, before the chapter's out, I think we're going to have a query where we ask for all the vendors that don't have any invoices. So we'll see that. But one aspect of a join is that you only get rows for the things that match. So we got a row for each of the invoices because they all match the vendor. Okay. We didn't get a row for all the vendors because there's quite a few vendors that don't match an invoice. Okay. So regular joins only bring back rows that match all the way across the join. Okay. Well, what do they match on? Well, we have these. We have this on clause. Okay, and it gives a condition for matching up the rows in one table with the rows in the other table. So what we say is we say on vendors dot vendor ID equals invoices dot vendor ID. So this says the primary key of the row on the vendors table has to match the foreign key of the row on the invoices table, and they're both called, both the foreign key and the primary key, they're both called vendor ID. Okay, so most joins that we do are just our way of implementing these relationships from table to table that are implemented with foreign keys. Okay. And then this one says order by invoice number. You may recall from the last chapter, I always like us to use an order by, even though you'll see examples here in the book where for MySQL we're not using one. In my class, I always would like us to use one. All right, so let's go on and see a little bit more, okay? Okay, now we're going to introduce a new kind of alias. Well, what's an alias? Well, in the old police movies, they used to say Tommy the Hood also known as Tom Smith, or Tom Smith, also known as Tommy the Hood, right? So that was an alias. It's another name that you're known by, okay? Now, the kind of alias we've had so far is it turns out that up in the select clause within the select list, we can provide aliases that are used as the column headings. And they really do, in some sense, become the new name of the columns. And this we found especially helpful when we had column specifications that were formulas. Okay, so we didn't want the column heading to be a formula. We wanted it to be a proper kind of column name, and so we came up with this idea of having a column alias. Okay, now we're learning that we can have an alias for table names as well. And so table aliases are created in the from clause. So here's what they're saying. Uh, Select a list from table one. That's name of a table. And right after there's a two-letter alias. So that means from now on, I can use the character string A1 and table one interchangeably. Okay? And then we say table one join. See, even here they're putting the inner into square brackets because they're not encouraging you to use the inner for an inner join. Says join table 2 and then A2. So A1 is the table alias for table 1. A2 is the table alias for table 2. And then they have another join. Yes, we can join 3 or 4 or 5 or 6. We're going to be doing it real soon. So we say join table 3, A3. Okay, now, what I like about the table aliases that they've used here is that they're very short. They're a character or two. Because in most cases, the only benefit of having a column alias, a table alias, is that it's shorter than the table name. Okay? You may remember that we use the name of the table to prefix the name of the column. Okay? Well, when the name of the table gets pretty long, then these expressions, like the on expressions that control the connecting from table to table, they can get pretty long, okay? And column aliases that are either a single character or 2 or 3 at most become a really good way to make your code more readable, okay? And that's the primary use case for table aliases. We'll see one more use case before the lecture is over, but we're going to hold off on that. Okay, so here's an inner join, plain old mom and pop join, with aliases for all tables. Okay, well, how many tables are there? Well, let's just look. From vendors V, join invoices I. Well, there's only 2, okay. And for vendors, we picked V. For invoices, we picked I. We picked the first letter. And that's the usual practice, okay? So now, when we get to the on clause, instead of having to code on vendors.vendor ID equals invoices.vendor ID, it's a little shorter. It's v.vendor ID equals I.vendor ID. And when the names of the tables get long, you'd be really happy to have a 1 or 2 or at worst say 3 character table alias. Okay, and this just has a where clause and an order by, and it works the same uh, as if we hadn't had the table alias. We just get easier coding here on the line uh, with the on clause. That's all that's actually going on. Okay, and again, you may notice here that we're matching, we're connecting, joining actually is a real word. We're joining vendors and invoices. Okay. We saw before that we got 114 rows when we did that. Here we're only getting 11. And why is that? Well, because we have a where clause. Okay. And this filters out more of the rows from the result set. So there are only 11 rows that have a positive balance due. Okay, that's what's going on there. All right. Now, just because we can code aliases for tables, it doesn't mean that we have to. And it's also the case that just because we code a table alias for one of the tables, we don't have to do it for all of the tables. So we have here on slide 7 an example of a select that joins two tables, one of which they create a table alias for, and the other of which they don't. So what are the two tables? Well, invoices and then invoice line items. Okay. Now they decide to call this line items. This is a horrible idea. Okay. Why? Because it's too long. I mean, it's certainly shorter than invoice line items, but generally the style is a character or two or three. Okay. So, my practice, which I got from watching others, is to take the first letter of each of the words, provided that that's going to be unique. So if I had invoices and I wanted an alias for invoices, it would be I. If I had invoice line items, I would make the table alias ILI, invoice line items. Okay. It's easier if you do that, because then when you're looking at the aliases down in other parts of the code, you remember what the alias stands for. So this is his third edition of this book, and he's shown us this in all three. And I've said that it's a bad idea in all three editions. Okay. I would have called this either, well, I would have called it ILI. That's what I would have called it. Okay. And then he can say on invoices.invoice ID, because he doesn't have a table alias to use as a prefix for invoices, but then he can say line items.invoice ID on the second one, which again is not a lot shorter than invoice line items. Okay, so it's an interesting idea, I think, poorly executed. Okay, now we're finally seeing that we can put names of other database objects in front of the database objects that we're used to having in order to disambiguate them. Okay, and that's what we were doing back here in the on clause. We were saying invoices dot and line items dot. Because if you just say invoice ID equals invoice ID, it's going to say that's ambiguous and it's going to give you an error. So we've been doing this a while. We prefix with a name and a dot these names in order to disambiguate them. Okay, and we're seeing on the next slide that you can even um, you can even prefix a table name in order to say, oh, this isn't in the normal database that we're used to using. Now, in our class, when we say we want to use our database, I'm going to prefer you just to begin before the select, say, in this case, it would say use AP, semicolon, right? He's assuming that what we've done here is we've gone into Workbench over to that navigation panel where we see all of our schemas or database, and we've double clicked on AP. So he's thinking that the default is AP because of the way we double clicked in the interface. So now when he wants to join from another table, a table in another database, he can just prefix it with the name of the database. And this one is OM, it stands for order management. So he wants to join order management customers, okay, which he's going to use the table alias C for, with vendors V. So then he can say on V dot vendor zip code equals C customer zip. Okay, now that's interesting because remember all the ones we saw before, the names of the columns themselves were the same. Okay. And why were they the same? Well, we were navigating across a formal relationship in the database that was created by a foreign key and made sort of enforced by this thing that we're going to learn how to do in chapter 10 called a foreign key constraint. Okay. Now, are those the only ways we can join tables? No, we can do something that we call an ad hoc join, which is to say we've got columns on two tables that we believe are going to match up, okay? And we're just going to go explore that. Is it based on a foreign key relationship? No, okay? But there's nothing that says it joins have to use a foreign key relationship. It's just the way we do it, maybe 94 times out of 100. Okay, so this version that we saw on the prior slide, okay, where we're chasing down a formal relationship, and so we're saying invoices invoice ID equals line items invoice ID. This is the kind of stuff that we're going to be doing, 95% of the time. These are formal relationships, and this is how we take advantage of them in our select. Okay, what if we think that there's a relationship between columns in two tables that's not part of a formal relationship between the two tables, but we think, you know what? The vendor zip codes in the vendor table, they're the same kind of zip codes that we're using in the customer table. What if we try to find out which customers are in the same zip code as the vendors? Well, so these kind of things, they're not using a formal relationship that's in the database. The fields, the columns that we are trying to match, they're not connected by a formal foreign key relationship or constraint. But we're just trying to kind of mine through the data and see if there are relationships there, these ad hoc relationships that we would like to exploit. And here you can see that we get all of these. So we can see that in this particular situation, the vendor, Wells Fargo Bank, is in the same zip code as Kyle Marissa. We can also see that Costco is in the same zip code as Thalia Nafalte and Rashad Holbrook. Okay, and we can see one down here under uh, Wakefield companies. Now, how we're going to act on that, I don't know. You know, uh, perhaps somebody in the back office has some kind of interest in this and they're going to find some way to take advantage of it. I don't know what that is. Okay. So that's an ad hoc relationship. And it turns out that one of the tables is in a whole other database, and we don't have foreign key relationships across tables from two different databases. So this is an ideal opportunity to try to use a join to discover the usefulness of this ad hoc relationship rather than the formal relationships that we do 95% of the time. Okay, so here are two tables. We have a customers and employees. Okay, so we have a customer ID and employee ID. They're both, they're sort of interesting values, but I'm going to guess that they're not taken from the same value space, and so we're not going to be able to match on those. But we have a customer last name and a customer first name. The employees have a last name and a first name. We could probably catch the relationships here by doing a join on these ad hoc relationships. And then we can see what their department number is and their manager ID. Okay. So here's an inner join with two conditions. Okay. We're saying that we want to show the customer first name and customer last name from customers, table alias C, join employees, table alias E, where C, customer first name, equals E, first name. So we're not using the same names for the same kinds of columns. And C, customer last name, equals E, last name. Okay, and typically what we're trying to do is we're trying to get keys to match up. But if in fact you're trying to create out of a key, out of a first name and a last name, which is kind of a rough way to match things up, because we can have people with the same name, so we could get that. But of course, we want to match on both parts. So to the extent that we're considering these two parts of the name to make up a key, it's a multi-column key, and of course we have to make sure that they're both equal. So we use AND. Okay. And it looks like the only match that we got was for Thomas Hardy. Okay. And again, I'm not sure what we're trying to do there in trying to match employees with customers. Maybe, maybe we think that good employees shop at our business. Okay, maybe that's good. Maybe we think that this is an opportunity for someone to scam our business. So being on this list is bad. I don't know if it makes you a good employee or a bad employee. But in either case, we found you by doing a join using these ad hoc relationships, which are not formally documented in the design of the database. We just try to go discover what's going to match up on an ad hoc basis. Here's a self-join that returns vendors from cities in common with other vendors. Okay. Now this, you'll remember that I said just a little while ago that one use, the primary use of a table alias, is just to cut down on the typing that you have to do. Okay, especially if you have long table names and you can replace them with a single letter or two or even three. It's a lot less typing. And not only the typing, sometimes these table names can get so long that they make the code less readable rather than more. Okay, so that's primarily your use case for using table aliases, except this one. Okay, there are some very unique circumstances in which we want to join a table to itself. Okay, it's kind of tricky programming. All right, and so that's what we're doing here. So we want two copies of the vendor table. Well, are we allowed to do that? Yeah, we are. We just can't call them the same thing. So the only way to call them different things is to use table aliases. We're going to call the first one V1 and the second one V2. Okay? So could we do this without the table alias feature? We could not. Okay? So whereas this is an important use of the table alias feature, it's not what you're going to be using it for maybe 90% of the time. Okay? So what we're trying to do is we're trying to find vendors from cities in common with other vendors. Okay? Now, so we want to match one list of vendors and with another list of vendors. They just happen to be the same list, but since we use the alias, they look like they're different lists. And we want a list of the matches. Okay? Now, that's a real good trick, except for the following thing. The vendors are always going to match themselves. So, let's say that we have a vendor, XYZ Electric, okay? And it's in Omaha, Nebraska, right? Well, if you match it to the other list, it's going to be on the other list. And you go, oh, I've got two vendors in Omaha, Nebraska. And then you go, oh, you know what? That's the same vendor. So that's what I would call, and some other people call, a trivial match. So we don't want that. We want a way to look for the matches between the two vendor lists, okay? But we don't want to match the trivial matches. We don't want things to match themselves. We only want to get matches where we're getting matches to other vendors that are in Omaha, Nebraska. If we've got 3 or 4 or 5, then we're going to want to list them out. If we only match ourselves, that's not what we are looking for. It's just a trivial match. So how do we do this? Well, let's see. We want to list vendor name, vendor city, vendor state. Okay? And look at this word, distinct. I'll be back on that one, okay? So then we say from vendors V1 join vendors V2. Okay, that's good. And okay, so then we want the match. So we want to say on vendor city, on V1 vendor city equal V2 vendor city, and V1 vendor state equal V2 vendor state, and V1 vendor name not equal V2 vendor name. So we want the city to match. We want the state to match. But we're using the name as a way to make sure that we don't get something to match itself. Okay? Now, with me, I probably would have wanted to do that with the vendor ID, but the vendor ID is not showing as one of our columns. So the vendor name's probably a good choice. It's always a good time it's always a good decision to be using the columns that you're displaying. Okay. And then we want to order by vendor state, vendor city. Okay, that's fine. And what about the distinct? Okay. Um, well, we don't want duplicate rows. Okay. So we don't want the combination of the vendor name and the city and the state. We don't want that to match both ways. So I think this distinct, we'd have to test it. I think this is maybe cutting the rows in half. Okay. This is this way we're only going to get the rows from the left that match to the right and not left to right and then right to left as well, in which we're going to have duplicates. And the result is we get these. So we should always have more than one, right? So in Phoenix, Arizona, we've got Computer Library, AT&T, Wells Fargo Bank. In Anaheim, California, we've got Aztec Label, Blue Shield of California. And then in Fresno, California, we've got Abbey Office Furnishing, California Business Machines, and Postmaster. Okay, so altogether we've got 84 rows. Okay, now how would we get more? Well, we would get I think that if we took off the distinct, we'd get twice the number of rows. And then if we took off this last part of the on clause, where we say that we don't want the vendor name to be equal to the vendor name, we would cut it. I think that cuts it in half as well. Okay, so what we wind up is we use a two table trick. We use one table two times, known by two different aliases, and then we get the benefit of being able to do that, but we need to do two different things in order to keep from getting noisy rows in the answer. Okay. Okay. Now, a statement that joins four tables. Wow, that's a lot. Well, this is time for us to look at another. It's time to look at some other graphic to really understand how we can join two or more tables. So what I want to show you, and I've already included in this particular semester, I think I put a copy of the entity relationship diagram for the AP database and for the My Guitar database. I put them under week one. Typically I put them up there when we load the data for the databases. So here we are. Here's an entity relationship diagram, right? So normally when we are when we're joining tables, we're trying to join based on formal relationships implemented with foreign keys. Okay. Now, when we look at an entity relationship diagram, we can see the relationships between tables that are implemented with foreign keys, right? So, for instance, we have the vendors table, and it has a relationship with general ledger accounts, and if in fact you look down here, we have this default account number, and that's what's used to build this relationship to account number. Okay. Now, what's what's a more typical relationship? Well, we've got invoices, and every invoice is associated with a vendor, and there is a vendor ID, that's a foreign key, for which we with which we build the relationship over to vendors. Okay, so if normally when we do a join, we're trying to reconstitute these relationships, okay? The easiest way to think of this is that we're going to join adjacent tables, tables that are adjacent by virtue of having the relationship, okay? So for instance, if I wanted to get the invoice and the vendor, I would, in my from clause, I would say invoices join vendors on invoices dot vendor ID equals vendors dot vendor ID. Or if I wanted to use a table alias, I could use one characters down there in the on clause. Okay. So what I usually tell people is think of the query that you're trying to do, the data that you want to get back, and then build a query where you join things that are attached to each other. Okay, so for instance, if we wanted to have let's see, a query that we might have. Well, let's look at the one that we're about to do, okay? We're about to do, we're going to say vendors join invoices, join invoice line items, join general ledger accounts. Okay, vendors, invoices, invoice line items, general ledger accounts. Let's go look. Vendors, invoices, invoice line items, general ledger accounts. Okay, so we're going to join vendors to invoices. We're going to join invoice, and then we're going to join the results of that to invoice line items, and then we're going to join the results of that to general ledger accounts. Okay, now what do we join on? Well, we join on the foreign keys, right? So for instance, the foreign key that makes the relationship between vendors and invoices go is this vendor ID, okay? The foreign key that makes the relationship between invoices and invoice line items go is let me find it. Line items, foreign key, invoices. Oh, it's just I'm not saying it. Vendor ID, invoice ID. Terms ID. Oh, I'm sorry. This is so embarrassing. Okay. Well, it's a good opportunity so you can see it happens to you too. Okay. So this invoice line items is a table, a linking table between invoices and general ledger accounts. Okay. All right. So it's a linking table, an associative table. It implements a many-to-many between invoices and general ledger accounts. So we might have general ledger account 1 could be associated with 0 invoices or 1 invoice or 100. Okay. And then we might say invoice 123 could be associated with 1, the general ledger account, or 2 or 3. So it's a many-to-many. How do we make that happen? Well, we're going to be using this over and over again. We have a linking table or an associative table in between. It's got the many side up against it from from both of the relationships, and it holds the foreign key. Okay. So, for instance, uh, it holds the account number to build the relationship to general ledger accounts. Okay. It holds the invoice ID that builds the relationship to invoices. Okay. So that's how we go from one of those to the other. Okay. So between vendors and invoices, it's vendor ID. Between invoices and invoice line items, it's invoice ID. Between invoice line items and general ledger accounts, it's account number. Okay, so we're gonna go vendors, join invoice line items, join general ledger accounts. So these things, okay, are easiest to code when you code them in this sequence you can figure out from the diagram. Okay. Now, is it possible to put them in the reverse order? Could you say general ledger accounts join invoice line items, join invoices, join vendors? Yeah, you could. Is is it possible even to not have them in one of these kind of sequential orders? Yeah, sometimes you can get away with that too, because it turns out the server is really smart. Okay, and it can take some things that are not maybe easy for us to think of, or to code, or to read, and it can figure them out. Okay, but what I recommend to you is if you're thinking of the query as having some things from vendors and then some things from invoices and then some things from invoice line items and then something from the general ledger accounts, then code them in that order. This, join that, join that, join that. Okay. Now, I just want to point out that this design has two features that are sometimes confusing to people. Okay. We generally say that we don't need two ways to connect from a table to another table. So, for instance, if you want to know how vendors and general ledger accounts are connected in the data, uh, the normal way to do it is the way that we're going to do it. You go from vendors to invoice line items to general ledger accounts. Well, what's the nature of this other relationship, which seems like a redundant one? And we're going to find out that that's a bad idea. Well, it turns out for the convenience of the user interface, they would like when you bring up a vendor, when you say, "Oh, I've got a payment for a particular vendor," it would like to be able to populate the terms ID and the general ledger account number. It would like to be able to populate them as a default. Okay, because we tend to buy the same things from the same people on the same terms over and over again. So this would be an easy way to make the data entry work. Okay, if not for this relationship here, which shows the default account number, and then there's another one here that shows the default terms. If we didn't have them, we couldn't pre-populate the fields with the most likely value so that the user could go, "Oh yeah, this is the normal general ledger account. These are the normal terms. Fine, I don't even have to click on anything." Okay, so these are convenience items. They don't mean the same. Okay, this says, well, what accounts do we usually use? And this says, what terms do we usually get? Well, those are conjecture, right? The real facts are through this sequence that we're actually going to query when we get back to the slide, which is from vendors to invoice line items to general ledger accounts. That's where the real facts are, okay? These other two foreign keys are just a convenience for data entry. All right, let's go back and look at the slides. So we're going to join invoices to invoice line items. No, I'm sorry, vendor to invoices on the vendor ID. That makes sense. On to invoice line items on the invoice ID. And then on to general ledger accounts on the account number. Okay, so those were all formal relationships in the database. They were based on foreign keys, and you will notice that the field names are the same. In one case, it's the name of the foreign key column. In the other case, it's the name of the primary key column. Okay, and let's see what else we do. We say where this is the formula for current balance. Current balance is greater than 0. We already know that there are only 11 invoices where the current balance is greater than 0. We saw that a couple of slides ago. And then we want to order them by vendor name, line item amount, descending. Okay, and then we get that. So I'm sorry about that. Hang on a second. Where are you? Okay, we're back. My apologies. Okay, so that's pretty straightforward. Okay, so you can, don't let this make you crazy. Okay, when you look at the result set that they're trying to get, vendor name, it's probably coming from vendors. Invoice number, that's probably coming from invoices. Invoice date, probably coming from invoices. Line item amount, probably coming from invoice line items. Account description, that's probably coming from general ledger account. Okay, so then you just go, okay, we're going to bring up our drawing and say, okay, something from vendors, couple thing from invoices, something from invoice line items, something from general ledger accounts. Okay, and the easiest thing to do, even though you don't have to do it in this exact order, is to code the join vendors to invoices, invoice line items to general ledger accounts. You'll never go wrong that way. And then what goes, what fields go in the on clause? Well, what's the foreign key that makes each of these go? Those are the fields that go into the on clause. Okay, it's actually pretty physical, right? If you're using formal relationships and you can read the diagram, you ought to be able to kind of walk your way to it very easily. Okay, let's go back, take a look at the slides. Alrighty. Okay, now I just want to take something that we've been doing and give it a name. Okay, so let's go back a slide. Okay, this stuff that we're doing here to do the joins, well, I guess I'm going to have to go from the top to the bottom. This is the way we do it now. This is the modern way, okay? This is called either explicit join syntax or ANSI, as in American National Standards Institute, ANSI joins, okay? It's where we give the information for the joins explicitly in the from clause. and we tell it two pieces of information. We tell it the name of the table that we want to join, and also we tell it the conditions that have to be satisfied in order to match across and to connect up the rows. Okay? This has been around for quite a few years, and it is the greatest. All right? It's what I want you to do in our class. Okay? If you look on the grading rubric for all of our assignments, it says uh, uses, it says something like uses explicit join syntax unless otherwise requested. Okay, we're about to go into a slide where we're going to talk about otherwise. Okay, but this is the way that we do joins. Okay, it works very well. It's easy to read, it's easy to understand, it's harder to make a mistake. Okay, now we're going to get in the time machine and go to the next slide. We're going to go back to the day when I learned SQL and joins. We didn't have the explicit join syntax, or what's otherwise called the ANSI join syntax. We had to do everything in the where clause. Okay. And you might say, oh, well, Kevin, that's fewer clauses. Isn't that kind of lightweight and a good idea? And from experience, I can tell you definitely no, N-O, capital N-O, no. Okay. So we're going to show you the implicit join syntax for two reasons. One is you might have to maintain some old code. Okay. The explicit join's been around for quite a while. I mean, years and years. Okay. Like, for instance, when I learned the implicit join, that was 40 years ago. Okay. So, well less than 40, more like 20 or 18 or something like that. The explicit join's been around for a long time, considered the best practice really everywhere. Okay. Well, how can you join tables implicitly? Well, this was the original design for the language. You would say the list of columns that you wanted to get in the result set. You would say in the from clause, you would just name the tables, separating them with commas. You wouldn't say how they were joined together. Okay. Now, in the implicit join approach, the where clause serves two purposes. Okay. One is it serves the same purpose as the on clause does in explicit join syntax. It shows how the tables have to connect with each other to make the join work. And then the where clause also has conditions that can filter rows out of the result set that we don't want. Okay, like for instance, if we go back, we filtered rows out of the result set that didn't have a balance due greater than 0. Okay, that's all we do with the where clause. In the explicit join syntax, the right way, the way we do it, the way that you're going to do it, the where clause only has one purpose. It is to filter rows out of the result set that we don't want. Okay. And all of the conditions that we use for connecting the tables are explicitly identified in the from clause. Okay. Whereas in this old implicit way, emphasis on old-fashioned, not the way you want to do it, the where clause is playing two purposes. It's a filter for the rows that you don't want, and it's a roadmap for how to connect the tables. Okay. Now this one's not so hard because you look at this and you go, oh, well, gee, they're connecting the vendors table to the invoices table. Yeah, this is just connection. This is just to make the join work. Okay. But let's say you've got 6 or 7 or 8 rows in the where clause, which you can easily get. If you go back to a query like the one that we just saw, uh, you would have 1, 2, 3, 4 rows in the where clause. I mean, how do you know what does what? How do you read a query like that? Well, you have to study it compared to a query that uses the preferred explicit join syntax. Okay, so here they just listed the tables out. You can have table aliases if you want, and then you have to put all the logic into the where clause. Okay. Here's another one. This looks pretty much like the one that we just had. So how many conditions are we checking in the where clause? Well, I predicted there was going to be 4. So we've got 1, 2, 3, 4. Okay. The first 3 do the connecting for the join. The fourth one filters out rows that don't interest us. Okay. And then the rest of the rest of these things are pretty much the same. Okay. Now this is an interesting idea. Let me tell you, the old days were harder than the new days. So unless I'm explicitly saying that I want you to do an implicit join, which I think we do in the homework assignment, then we don't want to see this. Okay. Let's go on. Okay, so terms to know about inner joins. The first one, inner. Inner joins are just plain old joins. Okay, that's what they are. You never have to use the word inner explicitly. Okay, you might use it in a sentence when you're speaking with your colleagues when you want to make a distinction between plain old joins and these outer joins that we're going to learn next. Okay. But in your code, will you code the word inner? I don't. Okay. And when I see it in others' code, I think it's just kind of verbose. Okay. So I don't really recommend it. Okay. What's a join? Well, it's a way of retrieving data from 2 or more tables in a controlled way where we are telling the database server how to connect each table to the next. Typically, we're doing that on formal relationships that are in the database that are based on foreign key connections and foreign key constraints that are formally in the database. But it could be from time to time we're going to do an ad hoc join that's not based upon a formal relationship, where we're just kind of we're going to go exploring, see if we have any customers that are our employees or something like that. We talked about inner join. An ad hoc relationship is a relationship, again, that is not enforced by the database infrastructure. So we don't have an explicit foreign key relationship, which is governed by a foreign key constraint that we're going to learn how to code in chapter 10. Instead, we've got 2 columns or 2 sets of 2 columns or whatever. We've got columns on one table that we think should match the columns on the other table, and we're just going to go explore that. A lot of times the names of the column in one table are different than the names in the other table because we're going exploring. Okay. A qualified column name has the name of a table in front of it. Okay. It might have, instead of the name of the table, it might have an alias. Okay. A table alias. It could even have a database a name. There's nothing that says uh, that you can't say database name dot table name dot column name. Okay. There are aliases for tables. There aren't aliases for databases. There aren't aliases for columns. What's a schema? A schema is a set of rules that govern your database. Okay. We're going to learn how to code them when we get to chapter 10. Okay. In MySQL, MySQL uses the name schema and database interchangeably, but that's just kind of shop talk for the MySQL people. They don't actually use them as interchangeably in other products. What's a self join? Well, this is where we join a table to itself. And you'll remember, in order to do that, we had to give that table two different table aliases um, in order to hide the fact that we were joining a table more than once. Okay. What's explicit syntax? Well, it's part of the SQL 92 standard. So if that came along in 92, that would be what, 17 years ago. All right. That's when it got into the standard. Okay. That's the right way to join things. Okay. What's implicit join syntax? It's the old way to join things. It's old fashioned. It's error prone. It's not good documentation. So don't use it unless you're explicitly asked to. Okay. Okay. Outer joins. All right. What in the world is an outer join? Well, I'm going to show you what the results of an outer join look like, but before we go through um, and try to look at the uh, components that make it work. Okay. Here we have a vendors and invoices table. Okay. So if we just look, there are 202 rows. We're only seeing the first five. Okay. So for the first one, we have the vendor name, Abbey Office Furnishings. We have an invoice number and invoice total. So there was at least there was one invoice for Abbey Office Furnishings. What about American Booksellers Association? No, there were no invoices. Okay. Now there are times when we want to know this, right? Um, well, let's think with accounts payable. Um, we have some vendors when we're operating a small business. I think these are actually the vendors that the Murach publishing companies were using at one time long ago, right? And so there are some people with whom you do business all the time, okay? And then let's say when you're getting ready to pay your bills for the month, you go, you run a report like this and you run down and then you go, oh, I don't have anything for American Express. I know we used American Express. Geez, looks like either we didn't get the bill or we didn't put the bill into the system. Okay. So that's the kind of thing where you would want to see all your vendors and what the invoices were. The other thing would be, let's say we looked at Abbey Office Furnishings and we said, oh, gee, there's one invoice for Abbey Office Furnishings, but I know we ordered two or three things from them. So let's go find out where those invoices are too. So this is a typical thing where you not only want to know what you have, but you would like the result set to remind you about things that you don't have. Okay? So, uh, how do we do that? Well, we need to be able to say across a join. The normal rules are we need a match between the left table and the right one. Okay. And left and right is uh, the first one in the sequence and then the second. So that's the way things kind of turn out in the output. So we say, if we say that we're getting it uh, from A join B join C join D, then A would be the left, B would be the right. Okay. Uh, and on and on. Okay. So what we typically do, the way we normally organize this kind of report, is we put the table on the left that we're most interested in. In this case, it's the vendor. And we want to be able to say, I want all the vendors, even if they don't have a match in the invoices, because even though the default is I'm only going to get the vendors who have invoices, that's not enough for the use case I have right now. I want a reminder of the vendors that don't have invoices. Okay, so here's what we do. We say from vendors left join invoices. That's it. So what's a left join? Well, a left join, it turns out we're going to see, is a left outer join. So it's the opposite of that inner join that we had before, or plain old join. And it allows one of the two tables to not match. Okay. And if we say left, well, the table on the left doesn't have to match. If we say right, well, the table on the right doesn't have to match. Well, do we really need left and right? Well, for me, not. I've only used right join a very few times in my career because think about how we organize reports. If we have a report like this, where we're going to have all the vendors and then the invoices and the invoice number in total, if we have any. Well, typically the way that we work in the United States and things are written top to bottom, left to right, we would put the vendor name on the left side. Okay. So generally speaking, when we're going to do an outer join like this, most of us who are trying to design the output to be useful to American business people. Okay, now this might not be true in all cultures, but the one where I have the most experience is the US. Most of us would put this column that we're going to list the rows regardless of whether they match across. We'd put it on the left side. Okay, so we would say vendors left join invoices. So we're going to get all the vendors and the invoices that match. And what happens when we have a vendor that doesn't have a match in invoices? We show a null. It's just empty. Okay, and that's enough to say, oh boy, I ought to look for that American Express invoice. And the way that we designed the report here, where we would have multiple lines for Abbey Office Furnishing, if we had 3 invoices for them, we would have 3 lines. This report, the way they designed it, it would tell you, it would jog your memory if you were expecting multiple invoices from Abbey Office Furnishings, and so far only one has showed up in the system. Okay, so this isn't like every query that you're going to do, but there'll be a lot of these. I mean, there are all kinds of things. A classic thing that I learned on was this whole data store about Italian operas. I have a friend who created it, and he's very interested in Italian operas. And so he built this whole data store and the relationships because it was sort of a hobby of his. But a lot of us taught with it for a long time. And the information that they had in the data store included uh, for each opera where it debuted, right? And in what city, right? So they wanted to create a report by city of how many debuts they'd had of Italian operas. Well, uh, you know, uh, uh, some big Italian opera cities had like 20 or 30 or whatever, but Poughkeepsie, New York had zero. Okay, well, it was the same deal. You had to have a non failing query on the left part in order to get a row in the answer set that said Poughkeepsie, New York, zero. Now, they may have had all the opera debuts in the world. I don't know, but that's the kind of thing we're looking for. So this comes up in the business of your organization reasonably often. And when it comes up, which the light that should go off is, oh, this is an outer join. Okay. Now, if we go back and we look at the syntax, we can say either left or right, and we can say outer if we want. Okay. Uh, Typically, I don't coach people to say outer because if you say left, it implies outer. If you say right, it implies outer. Okay. So typically, I tell people just code, for instance, left join, right join. So what did we do here on this one? Let's look. We said left join. Okay. So that's a left outer join. That means that the table on the left is non-failing. We're going to get the row whether it matches across to the table on the right or not. Okay. That's all that is. It's pretty cool stuff. Okay, so that's a left outer join. Um, and as I mentioned previously, do you have to know how to do a right outer join? Well, the thing for me is that I can't think of a right outer join, right? Because I think of creating a table like this where I have a full column on the left and then I've got some empty places on the right. Now, I'll show you another result set here in a minute where it's a little bit more confusing than that. But for me, this is a very well designed output, okay? And for me, those more typically use left joins than right joins. Okay, so here's one, here's some data. We have a table of all the departments: accounting, payroll, operations, personnel, maintenance. Now we have a table of all the employees, okay? And we know what department they're in because we have a foreign key that points to the departments table, okay? And then we have a projects table, okay? And this makes a many-to-many relationship go. So it has one row for each combination of project and employee ID. Okay, so that's how you can have one employee can be on many projects, and one project can have many employees. It's a classic associative many-to-many table. Okay, so let's look at what we want to do. Here we're looking at departments, left join employees. So we want to show all the departments and the employees that match. Okay, and we're showing a department number, last name. Okay, so here, interestingly, The only thing where we don't get a match is the maintenance department is a department. No, I'm sorry. Is that maintenance? No, I think it's operations is a department three. Uh, no, it doesn't have any employees. Whereas the payroll department, department two, has got three: Smith, Simonian, and Aronson. The personnel has two, but operations doesn't have any. So that's a classic left join. Okay. These things are often helpful when you're trying to populate your database and you know that things should be connected up. Like you shouldn't have a department without any employees. And then you use the query to show the departments that don't have any employees. And you're like, I think we need to put more employees in because I know we have operations employees. So either we're missing employees or we miscategorized them. Okay. So right outer join. Okay. Now this is something that I wouldn't do. Why wouldn't I do it? I don't like this report. I don't I don't really know. Well, I guess I do here. This says um, this says that I've got employees. Okay, I have an employee Watson who's in Department 6, but I have no Department 6. Okay, that's a database integrity issue. Okay, because of the way that we learned how to create these uh, constraints on these relationships between tables. Okay. And we're really going to learn that when we get to chapter 10, I guess. Um, when we set up a foreign key constraint and we go to insert Watson and we say they're in Department 6 and there is no Department 6, that sucker's going to blow up. Okay, it's not going to happen. All right, so I don't know why we need to run this. Okay, this should be impossible. All right. So I don't really like these things that look like this. I think, can you have situations like the one that we just saw? Yeah, you can. You just forget to add the employee from operations. On the other hand, should you ever get into the fix that they seem to be here on slide number 21? No, I don't think so. But what they're saying is that we're going to list all the employees because they're on the right and only the departments that match. Well, like I said, if we set the database up the right way with the right foreign key constraints, we could not have either Watson or Lecario in Department 6 when we didn't have a Department 6. Because the other thing that it would keep us from doing, if we had a Department 6 when we added them, this database referential integrity would prevent us from deleting up Department 6 as long as we had the rows for Watson and Lecario still pointing at Department 6. So this is, the use for this query is pretty speculative. Okay. As I said, most of my outer joins, given the way that I like to organize my data, are left joins. Join three tables using left outer joins. Now this is interesting, okay? It is possible to have some relationships, okay, where you might not have any data. So could you have more than one left join in a row? In this case, they've done it. So they took the departments, they left joined employees. So we get all the departments, and then the employees that match, and if we don't have any matching employees, we're going to get a null. And then the projects that match the employees, and if the employee doesn't have a project, we're going to get a null. Okay, so what does this look like? Well, the first row makes a lot of sense. We have Hernandez, uh, she or he is in accounting. They're on project P1011. Maintenance has Hardy, but Hardy isn't on any projects. Operations, as we already know, doesn't have any people. So if they don't have any people, then they don't have them connected to projects. The next one, the payroll people are all on the same project. Uh, Personnel has Jones, but Jones is not on a project. And personnel has O'Leary, and they're on project 1011. Okay, so this is sometimes it's hard to read these kind of reports, right? But it's a sensible report where we did left joins all the way across. All right. Combining an outer and an inner join. Okay, well, this is done really often. So we have the departments, we join to the employees, and then we join to the projects. So we're going to get the departments, but if we have a department that doesn't have an employee, like operations, we're not going to get a row for that department. Why? Well, we didn't force it with a left join. We just did a plain join. Okay, so you notice operations isn't in here. Okay, but then we did so that was between departments and employees. Then we did a left join to projects. So here we're getting all the departments and the that have employees, and then we're seeing do they have a project? And if they don't have a project, then we're going to get null. Okay, so that was a regular join and inner join followed by outer join, left join. Okay, now the next feature that we're going to learn is pretty easy. It's one that I favor, but it's a matter of style, and that is you'll remember that because most of the joins that we're doing are based upon formal foreign key relationships. Because of that, most of the names of the columns in the on clauses are the same in both tables. Usually their prefixes are different, but the tables, but the column names are the same. Okay, not always, but most of the time. Okay. Well, instead of saying on table A dot employee ID equals table B dot employee ID, you can say, for instance, well, here it was the vendor ID. We say from vendors join invoices using vendor ID. So we know what table, what two tables vendor ID is in. But if the name's the same on both of the tables, you can use this kind of shorthand. You can just say using vendor ID. And one of the things that I like is it's fewer characters to type. It emphasizes that they're both the same name. That kind of emphasizes that it's a formal relationship between the tables that is policed by a foreign key constraint, which admittedly we haven't learned how to create yet, but trust me, we will. Okay, so I like this. Okay, is it more efficient or better code than using the sort of on clause equivalent. It's not. It's a stylistic difference. So I would say the following thing. Discover your style and use that, except if you're answering an exercise that says, show us how to use the using clause, in which case we want this syntax right here. Okay? I like this. Not everybody does. Okay? But it's one of my favorites. Okay, let's go on. Is that it? That's not it. Okay. So here's using the using keyword to join three tables. So when you join three tables, you need two conditions. And in this case, they express them both with using. Okay. Now, this is kind of like the rule that we had with the table aliases. If we use using in one joint, do we have to use it in all the joints? No, we don't. Now, I think there's the argument that says you ought to use a consistent style, right? So there's a lot to be said for that. But as for the validity of the code, you can use using on one, on the next, using on the next one, on the next one, using on the next one. There's nothing to keep you from mixing and matching. Okay. Now, there's another option here that some people like. I'm not a fan of. It's called the natural join. Okay. So what we've said here is from table 1, natural join table 2. Well, what are we matching on? Okay, what natural join implies is look at those two tables and columns that have the same name should be equal. Okay, well then, so the like when we're doing a plain old join, right? Normally, it's on the basis of a formal relationship. Okay, we're matching a foreign key on one table to a primary key on the other table. They've got the same name. Okay, if we said natural join, okay, instead of saying on one table dot column name equal the other table dot column name, or we said we used the last option that we had, this using. If we did that, it would explicitly name the columns. Okay, here, in order to figure out the columns that are going to be used that have to match, you have to go look at the list of columns in both of the tables. So is it less to type? Yeah, it's less to type. Okay. Is it good documentation? I think it's kind of hazy documentation. I would rather see either the on clause or the using clause, but the natural join, which will do essentially the same thing if the columns are named exactly the same. I think that's a bad idea. Okay, I'm not going to encourage you to use a natural join. Well, why do we teach it? Well, we teach it because you may inherit code that somebody put a natural join into, and you've got to figure it out. I don't think it's a polite thing to do to people who come along to maintain your code after you, but maybe you think I'm a stick in the mud. I don't know. I would say stay away from them if you can. So let's see, they're selecting invoice number, vendor name from vendors, natural join invoices, vendors and invoices. What are they going to have in common? Vendor ID. Okay, so this would be the same as saying on one table vendor ID equals the other table vendor ID, or using vendor ID. Okay. Again, you get that result, but it's not very well documented. Oh, natural keyword in a statement that joins three tables. So we've got departments, natural join employees, left join projects using employee ID. Okay? So you can mix and match these things. Of course, the natural join between departments and employees would be department ID. Okay? So that's what's implicit in that natural. And then here we did a left join. We want all the departments. Okay, and then we did a left join projects. So what I don't like is I don't see operations, right? We said it, we did departments, natural join employees. Okay, so between a department and an employee, we have a plain old inner join. So that's why we don't see operations. But then we have a left join on the last one, so we can see the employees that don't have a project. Okay. Okay. Now, one of the reasons that we got away from using the implicit syntax for joins, the old-fashioned one, is we would unwittingly forget to put the information in the where clause that controlled the join, and we would get this thing called a cross join. Okay, and if you want a cross join, it's a beautiful thing. Okay, but generally you don't. Okay, why is that? Well, here's what you get. You get every permutation of the two tables. So here, for instance, we've got 45 tables are coming out in this cross join. The way that we got it is we cross joined a table with 5 rows times a table with 9 rows, and it takes every permutation. So you get 5 times 9 rows of output, you get 45 rows of output. That's not too bad, right? What if we had 100 and 100? Well, we'd have 10,000 rows. What if we had 100 and 200,000? It'd be astronomical. So the problems that we had with these things back in the day is we would be working with a tool like this. We would be working at the command line. We wouldn't have a nice graphical version of something like Workbench. And we would accidentally forget to put in the conditions into the where clause to control the join. We would send it off to the server, and then the server would just chunk, trying to come up with all the rows. And of course, we didn't even want all the rows anymore. Pretty quickly after we made that mistake, we realized, oh, I forgot to put the things into the where clause. Now, are there times when you want to cross join? Yeah, there are. Here's the classic for me. Let's say we're in the retailing business and we're retailing t-shirts. And the t-shirts for us come in 4 sizes, extra small, small, medium, large, and extra large. That's 5 sizes. Counting them on my hand. They come in 5 sizes. Okay. And let's say they come in 5 colors. Okay. And I'm going to leave the colors up to you so I don't accidentally give you 6. Okay. And, let's say that you want to see all of the different combinations. You want to see an extra small red, and then you want to see a small red, and then a medium red, and a large red, and an extra large red. Well, this is the ideal thing for cross joins. Okay, you have 5 times 5, you expect to get 25 rows, and you don't have to say it in a really, um, I mean, if that's what you want, if you want one times the other, if you want all the permutations, this is beautiful. Now, when you take these, uh, when you do a true cross join, which is what we're talking about here, you get this thing that we call the Cartesian product, okay? Which is, again, if you've got 5 rows and 5 rows, you do a cross join, you get 25 rows in the result set. That's the Cartesian product. If you've got 5 rows and 9 rows, you get 45 in the result set. And if that's what you're looking for, that's great. Unfortunately, in production databases in the real world, people don't usually want to see all that much data. They don't typically have a question where they want to bring back that much. They usually ask for it accidentally. So what we've done is we have an explicit way for you to ask for a cross join. You just say, for instance, so we want to select department number, department name, employee ID last name from departments cross join employees. So we're getting for department 1, we're getting accounting and then all the employees. Okay. Now, what's weird here is that do we really want that? Do we really want all these employees in all these departments? We probably don't. This is probably gibberish. Okay. But I think my example where we wanted to create a listing of all the combinations of color and size, I think we might really want to do that sometimes. Okay. And maybe we would want to know how many shirts we had in each combination of color and size, right? That's a cross join. So you explicitly ask for it by saying cross join. Okay, that's it. There's no on clauses. There's no where clauses. It's just you say cross join. Could you subtract rows out of it with a where clause? Yeah, you could. Okay, but there's no on clauses. Okay. Let's see. Terms to know about other types of joins. An outer join is a what some people call a non-failing join. You identify either the table on the left or the table on the right. You're essentially saying, I want all the rows from that table. Okay. So a left outer join, you get all the rows from the table on the left. A right outer join, you get all the rows from the table on the right. Okay. I prefer the one on the left because that's the way I think that good result sets are organized, right? At least for people here in the US. What's an equijoint? An equijoint is what we've been doing all along, where we say where the column on the table on one table equals the column on the other table. We're joining on equal values. Okay, so most of the joins that we did were equijoins. Natural join, well, that's where the like named columns have to be equal. Probably not good documentation. A cross join is where we get all the permutations between the table on the left and the table on the right. That's known as the Cartesian product. That's generally not what you want. Okay, I can only really identify a couple of use cases where I truly wanted uh, 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 the rows that I wanted were the number of the rows on the table on the left times the number of rows on the table on the right. Usually that's a very big number of rows and many more than you're interested in. And that multiplication of all the rows on the left times all the rows on the right, where you get all the permutations, that's known as the Cartesian product. Okay, the last thing we're going to learn about is union. Union is pretty cool stuff. Okay, I can't say that you're going to use it all the time, but it does give you the ability to do some interesting things. Okay. Uh, okay, so what we're going to do is we're going to take a select and get the result set, and then we're going to union it with another select and that result set, and then we can keep on going. You can do 2 or 3 or 4 or 5. Okay, so what it does is it glues them together. It glues the result sets together. Okay, and is that always useful? No. Okay, but it turns out it's useful sometimes, and we'll show you a classic case where using the union operation is useful. Okay, so you have to follow certain rules in order to do a union, or the server's going to complain. Okay, so each select that you have here, it must return the same number of columns. So if select statement 1 returns 3 columns and select statement 2 returns 8, you're going to get an error from the server. So they have to have the same number of columns, okay? The corresponding columns in each of the result sets must have compatible data types. Usually, with the kind of trick that you're going to learn here, they have the same data types. So you don't have a problem there. And then the column names in the final result set, that's the result set of all the unions, right? They're taken from the first select clause. Okay, so these, you have to have the same number of columns. They have to have compatible data types. Often they have the same data types. And the names of the columns really only matter in the first of the selects, because your result set is going to be named according to those column names. So what could you do? Well, some tricky stuff. Okay. This is helpful to do something that we learn how to do a different way about halfway through the course. Okay, there are times when you want to take rows from a table and you want to categorize them. Okay, on the basis of some values that they have. So, for instance, the classic is in this accounts payable. We have some that are active and we have some that we've already paid. Well, we're interested in the active ones. They're the ones that we still have to pay. Okay, but then again, in related but kind of opposite application, we have these things where we send invoices to our customers, and this is called accounts receivable, not accounts payable. And we want to know how current they are. Okay, and we usually classify them by saying whether they've been outstanding for 15 days or 30 days or 45 days or over, or 60 or over. And why are we interested in that? Well, we're interested because we're going to go call the people who are the worst deadbeats. Okay, so this kind of classification thing, again, we're eventually going to learn another way to do it when we uh, when we get to this thing called the case statement, which is pretty far along in the course. But in the meantime, it's a great way for us to learn what you can do with union. Okay, so when you really look here, let's see. Um, these guys are actually taking this from two different tables. The first one's coming from active invoices. The second one's coming from paid invoices. Okay, so this isn't a case where we only want to categorize within one table. What we're doing is we're taking data from two tables and we are characterizing them on the basis of where they came from. The ones in paid invoices are going to get the value paid in the first column. The ones from active invoices are going to get the value active. That means unpaid in the first column. And then we're going to combine them and we can have a report where we can see that some of active and some are paid, but we're getting them in a single result set. Okay. Now, you remember the number of columns has to be the same. So we've active 1, invoice number 2, invoice date 3, invoice total 4. Okay, let's look at this. Paid 1, invoice number 2, invoice date 3, invoice total 4. And you can see the names of most of these are the same, so they've got the same type, so that's going to work. Okay. And then what are the column names that we get in the results set? Well, they come from the first one. Okay. So they're source, invoice number, invoice date, invoice total. Now, did we really have to code source here? Did we really have to give it a column alias in the second select? No, not really, because it's going to get ignored. We could have just said paid. Okay, this as a source gets ignored. Where does that name come from? Up here, the first of the selects. Okay, so again, this is kind of a categorization, but it's a combination. We're using a union to combine like data from two different tables. Okay, pretty tricky. Okay, now the next one, okay, they're coming from the same table. So from invoices. Okay, that looks good. We're characterizing the first one as active. We're characterizing the second one as paid. Okay, so that's like unpaid and paid. Okay, and what's different about these two, well, the where clauses. So the where clause on the first one, active, they have a balance due. That's what, remember, this formula is for, of greater than 0. And then the second group has a balance due of less than or equal to 0. Okay, and so now these invoices from the invoices table are characterized as either paid or active. Now you might say, would a query like this be useful in the same database as the last one? I don't know. I don't know what their policy is for when things move to, what was the other table? Paid invoices, I think. I don't know what their workflow is for that. Okay, but here, when they're in the same table, well, if it's in this, if it's in the invoices table, it probably hasn't been moved to some kind of a paid table. Okay, so again, this is true, the categorization of multiple lines, multiple rows in the same table. And this is a classic way to do it. Again, we do have a way to do this using this case statement that we're going to learn about uh, probably in about 5 or 6 weeks, something like that. Okay, here's a union that combines the result sets from the same two tables. Okay, so this is from invoices join vendors. This is from invoices join vendors. So you can do a union even when you've done joins. You just have to follow the rules. You need the same number of columns. They have to be of the same data type, and it's going to take the names from the first select. So let's see. The first group we're categorizing as 33% payment. The second group we're categorizing as 50% payment. And we've got the where clauses here. So this is kind of interesting. We're saying that the bigger, oh, yeah, so again, you have to remember this is accounts payable. This is where we owe our suppliers, right? So we're going to say if the invoice total is greater than $10,000, then we're going to pay a third of it. And then if we say if it's between 500 and 10,000, we're going to pay half of it. So we're going to pay a little bit to everybody and keep them happy. Okay. And then we have another one where we say if it's less than $500, we'll pay all of it. Okay. We're just trying to keep as many of our suppliers happy as we can. Okay. Because implied in this is we don't have the cash to pay all of them. Okay, so this again is a classic categorization scheme, and as long as it's all coming from the same table, we're going to learn another way to do it when we learn the case statement. Okay, so this is a union that simulates a full outer join. So it's the same as it's like a left outer join and a right outer join. Okay, folks, I'm going to say here that I don't have a use case for this. And as soon as the student comes up with a use case for it and convincingly explains to me that we have to know how to simulate a full outer join, I'll start teaching it more robustly. But until then, I'm just going to claim I don't have a use for a full outer join, so I can't subject you to it because I don't foresee you having use for a full outer join either. And that, I believe, is the end. Terms to know about unions. Union, okay, we know what unions are. They glue together result sets that are similar, and a full outer join is at least to Kevin an outrageous idea. And that's it. Okay, so there's a lot of work to do. Work on your exercises, the ones that are assigned as the homework assignment and the ones on the back of the book, and take it slow. Remember especially that you can build a join one join at a time. So if you're joining 5 tables and you can just write it all out and it all works just fine, well, that's great. But otherwise, join tables 1 and 2 and convince yourself that that's working. Add on the 3rd. Convince yourself that that works. Add on the 4th. Then add on the 5th. Okay? So don't feel that with these joins especially, that you have to code the whole thing and get it all to work right out of the blocks. So with that, those words of advice, I'm going to say bye until next time. Bye-bye.